Hi. In this video, I'm going to talk about electric power. So unless if these electrons, these free electrons are in a superconductor, there's always going to have some resistance. And when electrons are moving, they're always constantly in motion, right? When they're moving, they're going to feel this resistance and it's always going to dissipate some energy. Because of you have a resistance in it. So this rate of this dissipation of energy is called power. Okay, how fast you're dissipating that energy. This dissipation of energy, the power, it can be converted. You use the energy, and the energy can be converted into a work to be done, or it can be converted into different kind of energy. Like it can be converted into. So when it converts to a work, it can be converted into a mechanical energy, like doing a work onto like a turn on the motor or something like a mechanical energy, or it can be converted into light to bright up. You turn on the light, so you dissipate the energy, use that dissipation of energy, some portion into converts to a light, or it can be converted into a heat. So remember, the changing energy is always, you change into some kind of a different thing, so you do a work. So anyhow, this dissipation, the rate of the dissipation of energy is called the power. And we use the unit that's called watts. And it's the power. We've learned that too, the how fast you do a work, right? How fast you do the work. So how fast these electrons do the work. And it's a scalar. So yeah, I'll just write it into the whiteboard again. See? Okay. Here. So let's see, electric power. It's a similar idea as the mechanical power. It's the how fast you do a work. But you see, if it's unless superconductor, if it's a superconductor, which you have a zero resistance, right? Conductor, you're always going to have a charge, always moving charge, I should say moving charge. Moving charge always dissipates energy. And we say the rate of electric energy, rate of electric energy gets the dissipation. How we do the electric force do the work, right? How fast this electric force do the work is called electric power. All right. And how this work can be done mechanically, so it can be converted into a mechanical energy. Like you can turn the motor, or it can be converted into a heat. It can turn on the light. Just transfers to this, the electric energy transfers to all these kind of energy. And here, the power, electric power, which is P. And again, we use the unit that's called watts, right? Remember? Is equals to the voltage times the current. So P is equals to VI. So 1 watt is equals to 1 volts ampere. But you can also use the using Ohm's law. So equals to VI, but I is equals to V over R. So you can use this one in it to say power is equals to, it could be V squared over R. It could be, what is it? V equals IR, so I square R, all these values. So let's see one of the example. So when we talk about the brightness of the lamp, the brightness, typically for the, unless CW, CFL, brightness of the lamp is you look at the watts. Wattage, right? So if you have a 60 watts lamp compared to 60 watts lamp, compared to the 100 watts lamp, this is brighter. So you use the, you look at this watts for the brightness typically. So the more watts means more using energy, so there's brighter, it's brighter, right? So let's say if we have for 60 watts lamp, how much current? Pass. So to have the 60 watts lamp, how much current does it pass through? Here, you connect it to 120 volts outlet, right? So what it looks like is that you have a outlet, and you connect it, and then here we have a lamp, and it turns on the light, dun, yellow, and that's, let's say, but darker yellow is better. I'll just do this. It's a 60 watts. So how much current does it pass through? Connecting to the 120 volts here, 120 volts, right? Then P equals VI. So from here, I can say current passing into the lamp is the power divided by the voltage. So 60 watts divided by 120 volts. So how much current? It's 0.5 ampere passing. All right. So that's how you can calculate and assume how much current passing through. So that's how much current that it can tolerate too. So let's say if I bring this lamp or electronic device that has a 60 watts or something, let's say if I bring it to Europe, which has in Europe what is it, electric outlet is 240. It's higher, right? So then does it gonna operate? You have the hair dryer that has the 60 watts, which is a lot lower than a typical hair dryer. But you bring it to Europe, you're not gonna have much current passing because you have a bigger voltage, right? So that means that it doesn't do much energy. You can't use the hair dryer. Hair dryer is not going to be as powerful. But if you bring the one that's made for European brand to bring it here, it can draw too much current, and it's no good for your electronic device. It's the resistance that matters. Basically, you make a resistance that can draw whatever the amount of current to work the most, to performs the best with that current and with that voltage. So you gotta, when you bring in an electronic device to different countries or different area that has different voltage, you gotta think about that, right? Yeah, and lastly, I just should mention, just to confirm that you know that power is changing energy per time. How much you do a work per time. Same idea as a mechanical power. All right, so this is going to be the end of chapter 23, and then that we're going to cover for chapter 23, and we just talked about the electrical power. All right, so I'll see you in a discussion.